Well, let's go ahead and get started. We're going to talk today about the basic geology and related parent materials. So let's start with just an overview of Virginia and just look at the relief map. And obviously we have mountains to the western side of the state and the southwest side, and then more gently rolling Piedmont in the center, and then a coastal plain on the right. And this is how those physiographic regions can be drawn out and separated by the terrain, the differences in the terrain. And we'll go through these one at a time. I've included a map of the physiography of Virginia for you in case you wanted to take a closer look later on after the webinar, because again, these webinars will be posted. This is the basic geology of Virginia, and again, this is for your reference later on. But essentially, the areas that are in red, pink, and bright blue are underlain by hard rock.
Oh my gosh, boy.
Okay. And the areas that are in green are underlain by metamorphic rock, which has been deeply weathered and so seldom is exposed at the surface. And in the coastal plain, the rocks are very deeply covered by as much as 15,000 feet of sediment. Here's a cross-section of the state, and it shows those hard rocks that we mentioned just a minute ago, the ones that come out of the ground, and you can see them in dissected areas. And then the Blue Ridge is part of the region where the rocks come out of the ground in the Blue Ridge and can be seen. And then the Piedmont, they are very deeply weathered. And then to the right, then we have the coastal plain sediments. So let's start by talking about the Appalachian Plateau. So the sediment that was laid down that became the mountains west of the Blue Ridge was really eroded from two enormous mountain ranges that once existed. And those mountain ranges have now eroded away. I believe they were called the Acadian range and the Taconic range. And some people believe that they were as tall as the Himalayan mountains, which I think is just extraordinary. Rivers flowed to the west, and they laid down alternating sandy sediments near the river and on delta if the water was flowing fast. If the water was flowing slowly, then shales and mudstones were deposited either in backswamp positions or on the deltas where the water was moving more slowly. Coal formed actually started as just thick organic soils in swamps. And so after being deeply buried, all of these sediments, then the materials turned into rock. So today we have flatline bedrock in the Appalachian Plateau. We have sandstones that underlie the highest summits, shales that are interbedded with sandstone, and then we have some coal seams mixed in as well. Some of the rocks are white, brown, and others are maroon-colored mudstones because those formed during times when there was much more oxygen in the atmosphere. Well, the rocks that are most resistant to weathering will be the ones at the tops of the mountains, and these are typically the white sandstones. And white sandstone weathers less rapidly than brown sandstone, and that's why it forms the ridge tops. But most rocks at great depth are either gray or black in color. Well, here's the landscape in this flat-lying region, and you can see at the very top of the ridge where a layer of hard sandstone is outcropping. And that is why we have a very level summit at the top and not dissected by rivers. Here's what that ridge-forming sandstone looks like, and it's very, very hard and very difficult to weather. And you can see there's really almost no soil here at all. The only soil is occurring in these cracks in the rocks. Here's a coal seam on the lower left. And then you can see the interbedded nature of the sandstone, which appears as the white layers, and then the shales that are the darker colored layers in between. And the shale weathers and erodes more easily than the sandstone does. And in the soils where the rock forms from the material below, we call that residuum. And here's a picture of a sandstone soil that formed in residuum on a mountain crest. And you can see fragments of that sandstone up further in the soil, and proving that this soil material originated from the bedrock underneath it. And we call that residuum. Here is a picture of a soil that formed from shale, and you can see the shale layers in place just below. The sandstones form the tops of the ridges, the shale outcrops on the lower ridges, and on what they call shale barrens, because some of these are barely vegetated. They just don't hold much moisture. Well, here we have a picture of what's called colluvium parent material. And colluvium it is moved by gravity, and it collects in positions on the landscape where the slopes are more gentle. So once the sediment comes to an equilibrium with the slope angle that it's on, then it comes to rest and it stays in place, and then a soil begins to form. And so this material is moved pretty much rock by rock, particle by particle, and in a very, very slow manner over a long period of time. And evidence that it is colluvium is that you get a mixture of rock types that are not all the same size or shape, and they're not related always to the bedrock directly underneath them. The residuum, you can match the rocks to the bedrock underneath, but in colluvium you cannot. Now here's a picture of what gets laid down in the river terraces. And you can see the sand and the gravel that's been sorted out, different sizes. These are different flooding events, different energies of water, and then finally that stream is flowing on the solid bedrock that's found in the area. But you get a mixture of different rock types, but almost all of them are rounded. If it's a major river, the rocks will all be rounded. If you're at the headwaters of a stream way up in the mountains, you'll get a lot of angular rock because they simply just haven't been transported very far. All right, how about the ridge and valley region? We have the same rocks as the Appalachian Plateau at one time, or we did have them at one time. Now they've been folded and faulted due to continental collisions. We have limestone and shale that's been pushed up and over the top of the Appalachian Plateau rocks. And then as those carbonate rocks, such as limestone and dolomite, began to dissolve, the sandstone and the shale underneath is exposed, and that's why we have ridges that come out. And the ridges are made of the sandstones and shales, and the valleys are typically made of the limestone soils. So today we have limestone and dolomite, the carbonate rocks. We have large areas of acid shale. We have limestone and shale that's interbedded in many areas. The rocks are folded and may be at almost any angle. The parallel ridges have white sandstone at the core, and the mountains that cut at right angles to the other mountains are usually made up of hard and pure limestones and shales. Now, for those of you that are familiar with the Blacksburg region, that would include areas such as the area around Ironto. And then also when you get into areas like Purgatory Mountain, which is just where the James River cuts across the IH-81 near Buchanan. Well, those are very, very hard limestones, but you might notice that those rocks and those mountains cut at right angles to the other parallel ridges. Well, let's take a look at some of those ridges, and you can see in the upper right at the very crest of these narrow ridges you would find the hard sandstones, and on the lower flanks you would find the shales. So where you see these dissected areas, that's where you're finding the shale, and at the very ridge tops we're finding the sandstones. Here you might see that there's a very steep, in the lower left-hand corner, a very steep mountain front, and then a very gentle sloping area. This would be where the colluvium is. So the residuum would be up here in the steep areas, and the colluvium would be down here in the gently sloping areas. And you might ask, where are the streams? If we look in the lower right, this is one of those areas where the bedrock is very hard and pure, and you can see the limestone coming out of the ground. But where's the stream in this valley? Well, there may be a sinkhole right here, but for the most part, because these valleys are underlain by limestone and dolomite, there are sinkholes that open up. And so the water can just as easily flow down through the soil as it can flow across the surface. Another look at the ridge and valley, and again we can see where the shale bedrock occurs. It comes all the way to the top of this ridge and even in the lower parts of the valley. In the lower right-hand corner, we see where most of the farmland or pasture land is, and that's the soils that form over the limestones. Much more fertile soil in the valley. The infertile shale and sandstones are found on the ridges, and you can see how the ridges are parallel to each other. Again, you just don't really see streams flowing through the area very often. Lots of springs and lots of creeks, but not larger rivers too often. This is what the bedrock looks like, and it is very complex. The rocks are folded. Here you can see where this limestone is turned completely up on itself, tilted and flipped all the way back around. And then here you can see in the lower right-hand corner, you can see this hard white sandstone called the Tuscarora sandstone, and that's what forms the middle of the ridges because it's just simply made of material that does not erode or weather. Here in the upper right-hand corner, you can see the alternating sandstone in the large blocks and the shales that are the more red material and the smaller rock sizes in below. Well, here's the soil that formed in limestone. You can see some of the limestone at the bottom of the picture, and it's a nice orange to red soil, fertile, very good soils. Here on the lower right, we see a shale soil, shallow, steeper. It's just not as good a soil, and these shales tend to be very acid, and so they're very infertile. This is what colluvium in the ridge and valley looks like. And you can see an assortment of sizes and shapes of the rocks, and that's an indication that they came from different sources. This one's tilted at a different angle than this one. This one's going straight up and down. Here we see a wedge of colluvium that's very recent. But also notice that this part of the mountain may also be colluvium because you can see the scattering of rocks, different sizes and shapes. So probably we have soils that formed in two different layers of colluvium in the ridge and valley. Now this is the best I could do to find you alluvium. This person is putting a dye tracer in the water to see where this stream, if it sinks into a sinkhole. I believe that's what he's doing. But the important point is that you have a gently rolling topography over the limestone, and the alluvium is just this small little area where he is kneeling, and also this little area in front of you. Why don't we have larger alluvium deposits in the ridge and valley? It's because the water can go down just as easily as it can flow across the surface, and so we don't really get a lot of sediment that collects in these valleys from rivers. Well, the Blue Ridge and the Piedmont regions will combine the parent materials because the geology is so similar. So how did the Blue Ridge start? Well, they were, a lot of the Blue Ridge, portions of them, especially down at the Grayson Highlands, were islands that were offshore, or they were parts of the African continent that were pushed up and over the rock of the ridge and valley basement, where the continents collided. In other words, the ridge and valley goes underneath the Blue Ridge, and the Blue Ridge was pushed over the top. And we know this because just east of Montvale, you can go and you can find the ridge and valley shales exposed at the soil surface. And then you get into the Blue Ridge Mountains, Thomas Mountain and other mountains, and then you're back into the ridge and valley rock. Well, this collision between the continents caused volcanic activity and magma that cooled below the surface, and this magma and igneous rock are some of the more resistant rocks. And also rocks from Africa that were metamorphic or became metamorphic are now part of the Blue Ridge. And that would be mainly granite and granite and gneiss and schist. The igneous rocks form many of the ridges, and the Blue Ridge Parkway is a good place to go to see these igneous rocks exposed. We have highly metamorphosed rocks in the cores of the highest peaks, and if you drive across Afton Mountain, or through Afton Mountain, I guess, on IH-64, you will see the green colored rock that makes up the core of the mountain. And it is probably undergone multiple times of metamorphism. We have an escarpment on the east side of the Blue Ridge, and then a gently sloping plateau that slopes toward the west. And it was a general reversal of drainage direction from west to east during the formation of the Blue Ridge. Most of the rivers now flow east off of the steep escarpment. They've been captured by that steep escarpment. And whereas we can find sediment in the ridge and valley that eroded from the rocks of the Blue Ridge, and that's how we know that the streams used to flow to the west. Well, these are the landscapes, and again, you can see the highest peaks where most of the more resistant rocks are, and then the more gently sloping, almost plateau-like region to the west side. Again, another look at the highest peaks. This looks similar to where we went hiking last weekend at Apple Orchard Falls. And then along the Blue Ridge Parkway down in North Carolina, you can see where the igneous rock is outcropping. Well, how about the Piedmont then? If the Blue Ridge has essentially been a part of islands and parts of Africa that were pushed over the top of the ridge and valley rock, what about the Piedmont? Well, the Piedmont is actually more of a piece of Africa. And we have a large zone extending from the Blue Ridge all the way out to the edge of the current continental shelf. And that stayed behind when Africa was pushed away by a spreading seafloor. In other words, a rift valley opened up and lava began coming out of the rift valley, and it started pushing the continents apart. And so Africa was pushed away, but it left a large part of itself behind. Most of that material is metamorphic rock, but because of all the strain and stress and forces, igneous rock comes up and bubbled up through cracks and came all the way to the surface. There were once volcanoes in the region on the edges of where rift valleys formed. These rift valleys would be very similar to the valleys that you see right now in the in the basin and range part of the United States in Utah and Nevada. Apparently that's largely what the Piedmont looked like at one time. But these basins were deep valleys that were filled in with sediment. That sediment was deeply buried and turned to rock, and right now they are found, the Triassic basins are filled and are very difficult to tell as you're driving across the Piedmont when you're driving through metamorphic rock from Africa and when you're driving across areas that were once deep valleys, because the erosion has pretty much leveled everything off. But at one time there were volcanoes. And in fact, there happened to be a very large volcano right next to where Richmond is today. Okay, the Piedmont is gently rolling because much of the parent materials weather easily under the warm, moist conditions that we have. And because of the general lowering of the landscape, colluvium is a very widespread parent material. The major bedrock types in the Piedmont are gneiss, schist, slate, and then igneous rocks. Okay, I'd like to pause for a minute now and see if anybody has any questions. So I'm going to open up the chat line and see if anybody has a question about the presentation today or the material that we've covered. Please feel free to type in a question. Okay, if nobody has a question, I'll ask you a question, and I'll do that using the chat feature. So my question to people would be, what is the rock type that forms the peaks of ridges in the ridge and valley? Okay, is there anybody that can type in an answer to that question? And immediately got the correct answer, and that's sandstone, and that's correct. And in fact, most of the time, if you see the white sandstone coming out of the ground, a lot of these areas have been converted into state parks or federal land, and they're great places to hike. Dragon's Tooth is a good one. And again, we hiked up to Apple Orchard Falls, which was another beautiful area just the other day. So which regions were once part of another continent? So of the regions that we talked about, which two were once part of another continent and now have been grafted on to North America? Well, we've covered 4. All right. I got an answer, and that answer is correct. You guys are on fire. Okay. It is the Blue Ridge and the Piedmont, and that's correct. And again, the Blue Ridge is kind of a mysterious region because in places the rock seems to be fairly well connected to the Piedmont rock, and in other places it looks like it came from a completely different geologic age. And that would make me think, picture today, Japan. Now imagine if North America collided with Asia. Japan would be crushed up against the edge of Asia and then maybe pushed onto the top of Asia, or maybe the other way around. Maybe it would be pushed onto California. In any case, though, the islands off the edge of the continents, when the continents do collide, do get pushed up, or they get pushed down. In our case, they were pushed up, and that's why we have limestone in the ridge and valley, because it was pushed up from the continental shelf and then pushed over the top of the other rocks. And we're thankful for that, because that gives that part of Virginia good fertility. Okay, well, let's go ahead and continue our talk with the Piedmont, and let's take a look at what the landscapes look like. Well, you can see they're much more gently rolling than the Blue Ridge was. Again, very similar rock types, very similar parent materials. Here's a look at a soil that I think is largely residual. You can still see the folded bedrock evident underneath. This material has actually lost most of its cementation, and so this is called saprolite. But essentially you can see where the metamorphic rock was, but then you can see this layer of rocks toward the top. And in that layer there's an indication that probably those rocks were scattered throughout a soil that once existed and eroded away for the most part. So you might say that these are the remnants of the soil that used to occur above this, what used to be bedrock. And then we've had erosion. And now we have a new soil forming yet above in the sediment. To the right is a picture of granite that has largely been weathered. So somewhere right about here is where the granite occurs. And so there's no porosity in here. You can see where somebody scratched it with a knife or with a shovel, trying to clean it off. You can see where there are different minerals cutting across. But this is what igneous rock and granite looks like. And then this soil has textures that match it up. They're not very highly developed, and these rock types do match up with the rock types that are found below. So this is a residual soil from metamorphic rock and from igneous rock. And that would be true in the Ridge and Valley, or in the Blue Ridge or the Piedmont. Here's the soil that formed in colluvium, and there are multiple layers of colluvium. And again, we see a scattering of rock sizes and shapes, different types, different orientation, different sizes. And so there may even be 3 layers of colluvial material in this deeply eroded soil. And then the rivers that cut across the Piedmont can form some very, very large river terraces. Again, the one thing you see in common about the Piedmont and the Blue Ridge soils is how red they are. And so these soils are full of kaolinite clay, and it's not very fertile. It's not even as sticky as some of the other types of clay that we have, but very high in iron oxides. These soils have a lot of quartzite in them, in the alluvial soils, because most of the other rocks weathered completely away. So even if this river deposit, and this would be a major river like the James River, as the James River crosses the Piedmont, and you look in the river terraces, you see a mixture of rock types, but they mainly are very hard sandstones that came from the Ridge and Valley, or quartzite, which came from the Blue Ridge and the Piedmont. And this is very, very hard rock. A lot of sand and gravel is mined from the upper parts of these river terrace deposits, and in fact that's probably why there's such a deep cut in this soil, is because it's probably the edge of a sand mine. And then down below where you have the clayey material, well, that material's not very good for mining purposes, so that would put an end to their activity. But this is a pretty good example of a major river terrace. Minor river terraces, most of those are wet. They're sandy, they're not very deep, and you usually hit bedrock or rotten bedrock within a few feet, 3 or 4 feet. All right, well, let's talk about the coastal plain origins. So we had rivers flowing east from the eroding mountainous lands, and they covered the Piedmont and the Triassic Basin rocks, and the weight caused the rocks to tilt at a downward angle. So in this drawing, you see a picture. It shows where the fall line is. It also shows you relative sea level right now. So you can see that the height of the Piedmont, this is actually the Piedmont right here, the intersection of the Piedmont and the coastal plain. And there's no exact line that you can draw, but typically when we see rock exposed in the rivers, we know that we are at the fall line. And a lot of major towns were formed on the fall line, such as Richmond, Petersburg, Raleigh, North Carolina. You can go up to Washington, D.C., Philadelphia, Baltimore, and even actually New York City is essentially the same. All right, so the weight of all this sediment that flowing from the rivers, and it literally just took the bedrock that was underneath the Piedmont, and the weight of all of this material pushed down on it and caused it to bend at the fall line. And we know this shows that there is up to 6,000 feet of sediment here, but we know that these sediments can actually be up to 15,000 feet thick. And then, of course, they thin out as they go out into the continental shelf. Well, this is the coastal plain region then between the fall line and the current Atlantic Ocean. And you might notice that it's fairly level, but it's not perfectly level. There's actually 11 marine terraces recorded in Virginia and can be identified, and some of those occur in the Piedmont. So at one time, actually, the ocean spread all the way to the base of the Blue Ridge. The ocean has risen and fallen, and because of that rising and falling, it built level terraces when it was high, and then it erodes those areas when it's low. Right now, we know that the ocean is rising, but after the next ice age, it will begin to fall again, and we will have another ice age. We're more than halfway there now. Okay, so that's the story. Alternating layers of river sediments and marine sediments. So sediment coming from the Piedmont, sediment being reworked and leveled by the oceans. Well, the areas have broad level marine terraces, and a good example of this is the area near Windsor, Virginia, and it's very level. But then you also have very highly dissected areas of the coastal plains, and the older the coastal plain and the closer you get to the fall line, the more deeply dissected the coastal plain is, because the rivers are down cut into the soft sediments. There is no hard rock underneath the coastal plain except at great, great depth. And so erosion by streams is very easy. Okay. The fall line bedrock is exposed where the bedrock begins to dip. And again, we see this in Richmond is a very good place. They have a park where you can go and observe the igneous rock, and that's called the Petersburg granite that is exposed right there. Well, these are the landscapes of the coastal plain, and this is one of those broad marine terraces. So this would have been river deposited material that was then reworked and redistributed by oceans that would have tended to level things out. When we get very, very close to the current ocean level, we get marshes, and just a little bit higher elevation, we get tree areas, but as the sea level rises, the salt water comes in and kills some of the trees, and you can see that effect happening in the upper left-hand side. But what kind of soil is formed out here in the marshes is largely organic material, because the area stays so wet that you just get very, very thick deposits of dead plant tissue. Here is, on the right is shown a barrier island. You can see waves coming in from the ocean side. You have still water on the backside, so you get silts and clays deposited here. You get sands deposited on the front side, and then the dunes that migrate their way in. And because of the deposition by flowing rivers, we get sand and gravel, clay, silt, then more sand and gravel, silt and clay, and so alternating layers of materials. And then after many, many thousands of years or hundreds of thousands of years, then we end up with deeply weathered soils from these sediments. And so the process of forming these soil horizons tends to obliterate the very thin layering from the original river deposits or marine deposits. And we get better drained soils. This might be close to the Emporia series. We get soils that have old indications of high water tables. Some of these may no longer even be present, but the colors are behind. And then we get today's wetland soils, and they do contain gray colors that are indicative of current day saturation. And along the river terraces, again, the major river terraces, Then we get sand and gravel deposit that is mined and sold. Along the smaller streams, we also have alluvium. Most of those are wet. And so the alluvium in the smaller streams would not have as much gravel. It would tend to be more of the silts and the sands and the clays. So this is what the parent materials look like in the different physiographic regions of Virginia. So I'd like to open it up again now if anybody else has questions about the parent materials that we've covered. Essentially, we tried to cover the 5 physiographic provinces. We tried to talk about the residuum, in other words, soils that reside where the parent materials started. In other words, where their fathers started. Soils form from parent materials, and if the soil is in the same place that the parent material was, it's called residual. If that parent material moves down the hill under the force of gravity, we call it colluvium. And if that material moves into a channel and is picked up and suspended and then redeposited by rivers or flowing water, then we call it alluvium. And depending on which of the major parent material types you have, will go a long way toward determining what type of soil that you have. So are there any questions? Trying to give a presentation that fits conveniently into your lunch hour? Or if you're at home and enjoying this from home, well, that's fine too. But does anybody have any follow-up questions? Okay. Says the question is, the undulating terrain on the flanks of the mountains in the Ridge and Valley province, does this reflect alternating sandstone, perpendicular shales? Okay, I think what you're referring to was the pictures of the Ridge and Valley where it looked like drainage ways were extending all the way up toward the ridge tops. Then there were other pictures of the Ridge and Valley where it looked like there was a very smooth flank of material that had maybe collected on the foot slopes. And I think the difference is that when you have that smooth material or that smooth apron underneath the steep mountains, then you can assume that that is multiple layers of colluvium. When you have the drainage ways, which are the dissected areas, going all the way up to the tops of the ridges, you can assume that the parent material is shale. When the drainage ways only go halfway up the ridge side and then stop, you can assume that the parent material is dominated by sandstone in the upper part of the ridge. And if you have limestone that goes to the top of the mountains, and again, there's just a few mountains where that happens, then you have deep dissections that go all the way to the top also. The limestone forms the drainage ways, and the shale forms the higher ridges. You're welcome. I hope that made sense, even though I know that there's a lot going on here. In the coastal plain, would there be cases where soil colors are reflective of the original alluvium? I think that could be true. However, the soils in the coastal plain, depending on which part you're in, may be up to 1.8 million years old. And so I would think that during that 1.8 million years, we've had so many ice ages, so many times when it's either been much warmer, much drier, or even much wetter than it is today, that I would think that by now, near the soil surface, those colors have been lost or altered. In other words, the types of iron oxides may have changed. You've had weathering, you've had leaching, and you've had additions of other materials over time. You've had mixing. But I think if you were able to dig down deeply, no matter which part of the coastal plain you're in, you should eventually get to material that's fairly unaltered. And at that point, I would say that you probably could do some studies to match up the material to its source region. Now, that would depend on whether the stream that deposited it was a short stream or a very major stream. For instance, the James River flows across, and it starts in the Ridge and Valley, and it flows through 4 different physiographic provinces. So imagine mixing the rocks of the Ridge and Valley, Blue Ridge, and Piedmont together before depositing them into the shallow water at where would have been ocean at that time. I would say that mixing, that would be very hard to identify the origin of the sand, silt, or clay. You would be able, though, to determine the origin of the rocks that were carried in the river. Okay, here's another question about ancient marine deposits. Yes, there are ancient marine deposits. Now, as the sea level rose during the ice ages, and there have been 26 major advances of ice. So 26 times the sea level would have been at approximately, if you would assume that all of those ice ages were equal, there's been 26 times that the sea level has dropped about 300 feet from where it is now. And then probably 26 times or 25 times when the ocean has been maybe as much as 30 to 100 feet higher than it is now. And so when the water was higher than the land was, the ocean water, then you would have had wave action redistributing sediment. Now, whether any sediment would have come from deeper parts of the ocean and been brought onto shore, that's probably unlikely. More likely is that the wave action, tidal action, currents, and other things, storm events, would have simply mixed and homogenized and leveled the sediments that were brought down by the rivers before or while the ocean was at lower depths. Okay, this sounds like looks like a long question. Thinking about your comments regarding pedogenesis, which is the formation of soil, does the soil formation environment help you make decisions about contemporary hydric soil determinations? Very much so. Because if I am trying to compare residuum versus colluvium versus alluvium, it first helps me understand and relate collection of sediment and movement of sediment. If I get to a landscape position which is largely residuum, those tend to be convex or steeply sloping. Where I collect colluvial material is typically in a foot slope position, or it was a previous foot slope position. And in that case, if I'm collecting sediment, I'm probably also collecting moisture. And so I begin to look for wetlands at the contact between colluvium and residuum. And then when I get further down into the valleys and I find alluvium, then I again expect more water because I'm closer to the stream levels, either today's stream levels or ancient stream levels. And so I'm looking at more level landscapes and closer to the water. And so I think of increasing amounts of wetlands as I go into an alluvial deposit. This is especially true in the coastal plain. and the Piedmont. In the Piedmont, it's very difficult to find a wetland any place except in a stream valley or on the slopes just above the edges of the floodplains. Okay, and here's another question, and I really am enjoying these questions. And this will probably be the last one because I promised that I would give you a break time to finish your lunch and get back to work. But it says, the question is, we see dark colored soils in the coastal plain at higher elevations, such as the Chickahominy soil type. Okay, I'm familiar with that soil. How do we know whether those soil colors are from ancient sediment colors or recent weathering and chemical actions? Okay, so if we're talking about dark gray colors, then those are most likely due to saturation and reduction of iron. And I know the Chickahominy soil has some shrink swell potential in the subsoil. So when you get that soil wet, that water, the clay swells up and seals off, and then you get very, very wet soils. And in fact, then you can have standing water in places. Well, if you get standing water, you really inhibit the decomposition of organic matter. And that's when the soils begin to get dark, as in black, because of added humus. So the thinking about the longevity of organic material, unless it has been compressed into rock like coal, typically the dark colors that we see are from recent organic additions. They could be due to a mineral that called manganese that is black, but most of the time it would be due to recent organic material. Ancient organic deposits probably would have been completely decomposed by the microbes by now and would not persist for much more than tens of thousands of years. Now you say tens of thousands of years is a long time, but not in the life of a soil. Many soils in Virginia are hundreds of thousands to millions of years old. And so the organic matter that originally was deposited with that sediment would be long gone. All right, I'd like to thank everybody for tuning in today. And again, spread the word. If you think that an introductory level presentation like this would be of interest to your colleagues, feel free to share. And I will send out an invitation again in 1 month. And every month we'll have a topic. And I'm not sure quite what next month's topic is, but I took a poll and collected input, and I'll repeat that poll and give other people a chance to weigh in as to what kind of training they'd like to receive. I also do on-site training, and if you have the interest or your organization has the interest, well, feel free to contact me and maybe we can set something up. All right, if not, be very careful driving. Enjoy the snow, but be careful of the ice. And watch out for low temperatures. It's supposed to get to -10 tonight in Blacksburg. That will be the coldest that I've seen in Blacksburg, but I used to live in northern Montana, so not the coldest I've been in yet. Have a great day, everyone. Enjoyed our session today.